Hi friends, welcome to Circuit Tricks. In continuation to PLL lecture series, today I am going to cover how to analyze the PLL loop. In my previous lecture titled Phase Lock Loop Basics, I introduced key building blocks of the PLL and the basic operations of the loop. I would recommend you to watch that video before taking up today's lecture. The link is provided below in the description box. Let us get into today's lecture called Loop Analysis. Okay, so the essential element of PLL is VCO. So this generates the output clock frequency. We can say that as F out. The loop is generally analyzed using phase, so it is called as theta out. It has a control input. By controlling this VC, we can tune the frequency of the voltage controlled oscillator. So this VCO frequency changes over a period of time because of internal random noise or variation due to process, voltage or temperature. So this will be compared with the known reference clock whose frequency is FREF. This has a accurate frequency. So the phase of this reference clock is called as theta reference. So in order to compare this with the reference frequency, we need to bring the VCO frequency to the same value. So we will be using a divider. So generally the VCO output will be much higher than the reference frequency. Okay. So then this divided phase, we can call this as theta FB. So these two will be compared using a phase frequency detector. So this generates the error signal between the reference phase and the feedback phase. If reference is leading the feedback clock, then it will generate a up signal. If reference is lagging the feedback clock, it will generate a down signal. So then these two signals are used to control the charge pump. So this will up signal will control the charging switch and down signal will control the discharging switch. Okay, so this charge pump is connected to a capacitor where this charging current and discharging current will change the control voltage across the capacitor. So this voltage will be used to control the VCO frequency. Okay, so whenever the VCO frequency increases more than the reference frequency, then the down signal will be generated and it will discharge a capacitor and it will bring the voltage down so that the frequency matches with the reference frequency. So similarly, the opposite happens whenever F out is slower than the reference frequency, then up signal is increased and it will charge the capacitor and the VC increases and bring the frequency constant. Okay, so now let us draw the transfer function. Okay, so we will draw the transfer function block by block. Okay, so a phase frequency detector takes the difference between the feedback clock and the reference clock. So theta reference minus theta FB. Okay, and this generates the error signal called theta E. Then this has a gain of 1 over 2 pi. Okay, so then this goes as an input to charge pump. Charge pump and capacitor combination has a transfer function which can be given by ICP divided by S times C. Then this generates the control voltage VC which controls our VCO. The transfer function of VCO is 2 pi k VCO divided by S. Okay, so kV is the gain of VCO, that is the rate of change of output frequency to rate of change of control voltage. The unit for this is hertz per voltage. So here 2 pi is used. Here 2 pi is used to convert this into radians and integration is happening to convert this into a phase. So this generates my output phase theta out. Okay, so I have a divider 1 by n which transfer function is 1 by n. So now the whole loop will look like this. Okay, So now let us derive the relationship between the input to output. Okay. So there are two signal paths. One is signal coming from input to output. I will call this as forward path. And there is another path where the output, some amount of output is fed back to input. I will call this as a feedback path. Okay. So the forward path gain is given by the product of all these terms, that is 1 by 2 pi multiplied by ICP over SC multiplied by 2 pi kV over S. Okay, so we can cancel these 2 pi and these 2 pi, so the forward path gain will be equal to ICP into kV divided by S square into C, and feedback path gain is equal to 1 by N. Okay, so from so now let us derive the output to input relationship. So how do you uh, so, so output phase theta out of S can be written as input error signal theta E multiplied by the forward gain. So that is theta E of S multiplied by forward path gain. So this can be given as theta E of S multiplied by ICP into kV divided by S square into C. So theta E of S is the difference between theta reference of S minus theta feedback of S. Okay, so replacing that, we will be getting theta out will be equal to theta reference of S minus theta feedback of S whole multiplied by the forward path gain, that is ICP into kV divided by S square into C. Okay, so theta FB of S can be written as 1 over N times theta out of S. Okay, so here theta out of S can be written as theta reference of S minus 1 over N theta out of S whole multiplied by ICP into kV divided by S square over C. Okay, so now rearranging this and bringing this theta out in one side, we can get theta out of S whole multiplied by 1 plus, if this comes over this side, 1 over N multiplied by this ICP into kV divided by S square into C is equal to theta reference of S multiplied by ICP into kV divided by S square into C. Okay, so rearranging this, we can get the ratio between theta out over S divided by theta in over S. So this is called closed loop transfer function. Okay, so I will represent this with a G of S will be equal to ICP kV over S square C divided by bringing um, this term to this side, we will be getting 1 plus 1 divided by N into ICP into kV divided by S square into C. Okay, so here we can see that, so this is a forward path gain divided by 1 plus feedback path gain multiplied by the forward path gain. Okay, okay, I can represent this whole thing as H of S, which is given by the product of feedback path gain multiplied by forward path gain, which is ICP into KV divided by N times C into S square. So this is called loop gain. Okay, so if we replace this term with H of S, we can get the closed loop gain G of S as H of S multiplied by N divided by 1 plus H of S. Okay, so this is the closed loop transfer function of the PLL. So here we can see that if H of S is equal to minus 1, then G of S will go to infinity. That means the loop will become unstable, the gain becomes infinite. So the condition for instability is the magnitude of H of S equal to 1 and angle of H of S equal to 180 degree. So when this happens, the gain goes to infinity and the loop will become unstable. So if you see from here in this picture, okay, so whenever there is a forward path gain, if the gain of this loop is more than 1 and it in this process if it has 180 degree phase shift, then we have another 180 degree phase shift. Because of this subtraction, total we will be having a 360 degree phase shift. So this will result in addition rather than a subtraction. So this will lead to positive feedback. So the positive feedback will result in instability in the system. So in order to avoid and in order to make the system stable, what we need to do is we have to break these two conditions. Okay, so whenever the gain is greater than 1, the angle should be less than 180 degree, or whenever the angle is greater than 180 degree, the gain should be less than 1. Okay, so let us analyze this loop gain to see whether it will meet that condition or not. Okay, so let us rewrite this H of S here, which is ICP into KV divided by S square into N into C. Okay, so in order to do the magnitude, we replace this S with J omega. So magnitude, sorry, before magnitude, we will just replace this with J omega. We will be getting ICP into KV divided by N times C into 1 by J omega multiplied by 1 by J omega. Okay, so here we are dealing with a complex number. Let us quickly see how to take the magnitude and angle of a complex number. If you have a complex number C1 equal to A1 plus IB, then IB1, then the magnitude of C1 will be equal to square root of A1 square plus B1 square, and the angle of C1 will be equal to tan inverse of P1 over A1. Okay, if you have a complex number C2 which is in the denominator, so A1 plus IB1, then what you have to do is we have to multiply numerator and denominator by A1 minus IB1, its complex conjugate, divided by A1 minus B I times B1. Okay, so the magnitude of C2 will be equal to 1 over square root of A1 square plus B1 square, and angle of C2 will be equal to tan inverse of minus B1 over A1. As tan minus theta is minus tan theta, that will be equal to minus tan inverse of B1 divided by A1. So from here we can see that if the complex number is the numerator, it will behave differently or just opposite to that of if the complex number is in the denominator. So the gain will be inverse for the complex number in the denominator, and the angle will be negative. Okay, so here let us take the magnitude and angle for this h of j omega, which is a loop transfer function. Magnitude of h of j omega is equal to ICP over kV divided by n times c into 1 by omega square. Okay, so generally we represent magnitude in terms of dB. So h of j omega in terms of dB will be equal to 20 log ICP into kV divided by n into c. So this is a term which is independent of frequency, and we have another term which is 40 times log of omega. So this is a function of frequency. Okay, and how do you make the angle? So h of j omega angle will be equal to, so you have two complex numbers, so addition of two angles we can write here as minus tan inverse of the imaginary part is omega and the real part is 0, and minus tan inverse of again imaginary part is omega and the real part is 0. This results in minus 90 degree, minus 90 degree. So angle of h of j omega is equal to minus 180 degree. Okay, so now let us plot this magnitude and angle across frequency omega. Okay, so let us take the y-axis as magnitude of h of j omega, and the x-axis is frequency omega. And similarly, we will have another plot where the y-axis is angle of h of j omega, and the x-axis is again omega. Okay, so if we plot, if you see from this equation, as omega goes to 0, then this term goes to infinity, so the gain will start somewhere at infinity. And if you see here h of j omega, which is independent of phase, it will start from the value 180 degree, minus 180 degree. Okay, so we can see here as omega frequency increases, um, uh, the value of overall gain reduces because of this negative sign and with a slope of minus 40. So let us plot this. So we will be getting a continuously reducing gain with a slope of minus 40 degree. So let me redraw this as it is not a straight line. Okay, so this is called, this will be having a slope of minus 40 dB per decade. Okay, and frequency as it is independent of, sorry, angle as it is independent of frequency, it will remain constant at 180 degree. So then this is the frequency at which the gain reaches 0, is called crossover frequency omega c. Okay, so from here we can see that the gain is more than 1, or in terms of dB it is greater than 0 in this region, and the phase angle is 180 degree. And even though gain goes below 0 at these frequencies, still the phase angle is 180 degree, so the system will be is unstable. Okay, now let us see how to stabilize this loop. Okay, so by introducing a 0 we can cancel the effect of a pole. So essentially we have to introduce a left hand side 0. Okay, so how do we introduce a 0? Let us take a charge pump and low filter combination as shown over here. So this charge pump has a value of ICP on both charging and discharging sources, and it is controlled by up and down signal. Okay, so this goes and charges or discharges a capacitor, but by adding a resistor in series we can introduce a 0. Okay, so here you have an output voltage which is called V control voltage, which is given by sum of voltage drop across the resistor plus voltage drop across the capacitor. Okay, so VC will be equal to, if ICP is the charge pump current, then ICP multiplied by R, and V cap equal to ICP over SC. So essentially VC equal to ICP into R plus 1 by SC, which we can write it as ICP into SRC plus 1 divided by SC. So thus this system we can see has a 0 at omega z equal to 1 by RC. Okay, so this system has a 0 omega z equal to 1 by RC. So this is an important parameter which is used for controlling the stability of the loop. Now let us plug in this transfer function, okay, into our PLL loop and analyze the system. Okay, so first we will have a phase frequency detector whose transfer function is given as theta reference minus theta feedback multiplied by 1 over 2 pi. Okay, so this output goes to our charge pump and filter combination, which is given by ICP into SRC plus 1 whole divided by SC, and then this goes to VCO, which has again 2 pi into KV divided by S, and this is your theta out, and this goes and then controls the feedback through a divider with a value 1 by N. Okay, so now let us write the uh, loop gain. Okay, so the loop gain H of S is the product of a forward path gain multiplied by feedback path gain. So what is my forward path gain? My forward path gain is the product of all these terms over here, and my feedback path gain is the uh, product of this feedback path. Okay, so let us rewrite this as H of S is given by ICP into S or C plus 1 multiplied by KV divided by S square into C multiplied by 1 by N. So this is my feedback path gain, and this is my forward path gain. Okay, now H of S can be rewritten as ICP into KV divided by N into C. All these constant terms are brought back over here. S into RC plus 1 divided by S square. Okay, so now we have to analyze its magnitude and angle to see whether it will be stable system or not. So let us replace this S by j omega. So we will be getting H of j omega is equal to ICP into KV over N into C multiplied by j omega RC plus 1 divided by j omega into j omega. So what is the magnitude? So magnitude of h of j omega in terms of dV will be 20 times log ICP kV divided by N into C. Okay, plus, so the numerator term will be 20 log square root of omega square r square c square plus 1 minus 40 because of this denominator term. Okay, minus 40 log omega. And what is the angle? H of j omega will be written as here you have a numerator term and also a denominator term. So we have to add one by one. So that will be equal to tan inverse of numerator is omega RC divided by 1. So where omega RC is the imaginary part minus tan inverse of omega by 0 minus tan inverse of omega by 0. So we know that omega z equal to 1 by RC. So angle h of g omega will be equal to tan inverse of omega by omega divided by omega z minus 180 degree. Okay, so now let us draw the body plot, that is the magnitude and phase plot across different frequency. Okay, so here we can see that when frequency, okay, let us first draw the coordinates where y-axis is magnitude of h of j omega and x-axis is omega. And similarly we have another graph where y-axis is angle of h of j omega and the x-axis is again omega. So here we can see that as omega is 0, we can see that still there is a log 0 will be infinity. So the DC gain will be infinite, which will start somewhere at infinity. Then from here, from this term, we can see that as omega is very small value, then it will be almost equal to log of 1. So it will not add any impact on the gain at very low value of omega. As the omega increases, so this will fall at the rate of minus 40 dB per decade. Okay, until this omega in this zero term becomes more significant. Okay, and when this value become equal to omega c, it will become square root of 2. Then here we can say that until it reaches that value, so I can say that as minus omega z. Okay, so after it is reaching this, then the gain is a function of this plus this. So this has a total plus 20 dB roll off and this has a minus 40 dB roll off. So effectively it will roll up at much slower rate as minus 20 dB per decade. So here we have minus 40 dB per decade roll off and here we have minus 20 dB per decade. Okay, so now let us plot the phase. So phase, if you see, or the angle, if you see here at 0, tan inverse of 0 is 0, so it will start with minus 180 degree. Okay, so then as omega becomes equal to omega z, it will become tan inverse of 1, which is 45 degrees. So minus 180 degree so minus 180 degree plus 45 degree results in minus 135 degree. So at omega z, the value will be minus 135 degree. So that will be somewhere here. So then this will be like this. And as omega increases, as omega goes to infinity, tan inverse of infinity will be 90 degree, and at infinite it will reach 90 degree minus 90 degree. Okay, so this is the Bode plot for the system after introducing a 0. So now here we can see that this is the frequency which is called crossover frequency, where the gain is 1. At this frequency, if you see here, the phase is 90 degree. So this system will be stable. Okay. So there is a new term we will be introducing which is called as a phase margin. So how much it is away from 180 degree. Okay, if at the crossover frequency, if the phase angle is 180 degree, this will result in a oscillation. So the stability of a system can be measured by a term called phase margin, okay, which says how far it is from 180 degree. So phase margin is given by 180 degree minus all the uh, phase contributed by the poles and zeros at omega c. So replacing this omega with omega c, we will be getting this. Okay, so 180 degree minus so, uh, okay, 180 degree plus, so we have this angle, okay, which is tan inverse of omega c divided by omega z, and we have this minus 180 degree. Okay, so we can cancel these two terms, and the phase margin is given by tan inverse of crossover frequency to zero frequency. Okay, so this is an important parameter which essentially tells you how the system is, how much the system is stable. If we reduce the value of omega z, then the system will be more and more stable. Okay, so where omega z is given by 1 by rc. Okay, so this is the open loop or the loop gain analysis. Okay, now we will go back and then write the closed loop gain analysis. Okay, so closed loop gain is given by g of s equal to n times h of s divided by 1 plus h of s. Okay, so here we know that h of s equal to ICP into kV divided by n into c into s or c plus 1 over s square. Okay, so replacing that, we'll be getting g of s will be equal to n times ICP into, so I can take to make it simple, I can take this entire term as a value k. Okay, so then I can write this as k times s or c plus 1 over s square divided by 1 plus k times s or c plus 1 over s square. So we can rearrange this equation. We will be getting n times, bringing this k inside, we will be getting s or c into k plus k divided by s square plus s or c into k plus k. So this is of the form of famous second order equation, which is 2 delta omega n s plus omega n square divided by um, s square plus 2 delta omega n s plus omega n square. Okay, so this is in the same format. Okay, so what we can do is we can equate this omega n. So by equating this omega n to this k, we will be getting omega n, which is called the natural frequency of the system. Okay, is given by k. Omega n square is given by k, and which results in omega n equal to square root of k. And similarly, we can compare this 2 delta n with rck. So delta 2 times delta omega n is equal to r into c into k. Okay, so delta will be rck divided by omega n, and replacing this omega n with the square root of k, we will be getting rc into square root of k. So we know that k equal to ICP into kvco divided by n times c. So replacing this, we will get omega n equal to square root of ICP kV over n times c, and damping factor. So this is called damping factor. delta, which is given by 1 by 2 into, so this 2 also will come here in Mr. 2 into RC into square root of ICP into KV over NC, and we can rearrange and get R by 2 into square root of ICP KV into C divided by N. So these two are the important parameters of the PLL loop system. So remember these two, which will be useful in designing the PLL and understand its behavior. So we have analyzed the PLL loop and made it. By introducing a zero, we can make the system stable. So from the loop gain, we got two terms, which is omega z, which is given by 1 by RC, and phase margin, which is given by tan inverse of the crossover frequency divided by omega z, where omega c is when the magnitude of h of j omega c equal to 1. Okay, by equating this, we can get the value of omega c. So this is from the open loop. Okay, from closed loop equations, we got the natural frequency omega n, which is given by ICP into kV divided by n times c, and also the damping factor, which is given by r over 2 multiplied by square root of ICP into kV into c divided by n. Okay, so these are the essential equations you should remember, okay, which will be used for the design of the PLL. Okay, so I will stop here for today's lecture, and we will discuss about the loop introducing a noise in my next lecture series. Thanks a lot for watching this video, and if you like it, please hit a like button and also subscribe my channel. If you have any comments, please add it in the feedback uh, comment section below, so that will be helpful for me to improve my sessions. Thanks a lot for watching this video.